Good afternoon. Bonjour, PyParis. So it has been a fantastic conference so far. A lot of nice, interesting talks, especially in the data engineering area. So this talk also falls into the same area. In this talk, we will be talking about coding for cloud. I'm Harjinder. I'm from Red Hat, and basically in this talk, we'll see how to design and develop cloud-native machine learning application using Python. Bhargava Subramaniam is co-author of this talk, but he could not make it, so I'm going to hold the fort. Okay, to set the context, let me start with a simple story. So this is a story of Grace and Mark. Grace is a smart individual, and she has just completed MBA. Here, MBA is not market basket analysis. I meant Masters in Business Administration. Okay. And Mark is a geek, just completed the engineering. These two guys had some business idea and got decent funding from a VC who told them that this is an experiment, let's try it out. An experiment in double quotes. So VC told, let us try it out, implement this idea, and see how market responds. So they started the project. Grace says, hey Mark, we don't have enough budget to own our own servers. Why can't we rent some? Mark agrees. He knows that she's talking about cloud computing. And he remembers his favorite professor who used to teach him cloud computing. So professor used to tell him that cloud computing is nothing but rented computers. Very similar to the idea of car rental, like Europe car, movie rental, like Netflix, and so on and so forth. Also, in this context, let us see what cloud native application is. Being cloud native means we write and design our application mainly for running in the cloud, which is specifically targeted towards the cloud. Okay, so Mark implements the first version of the project and launches the service. Fine. So more and more customers are now using their service, they like it, and sooner they encountered a performance issue. Grace is somehow unhappy, and Mark is also confused because he had put a lot of effort in doing algorithm complexity analysis and so on and so forth. But he didn't expect this to happen. But then he realizes it might be related to some scalability issue. Okay, so then basically he calls his professor and discusses this idea. And professor suggests that this looks to be a scalability issue. He suggests how to tackle this kind of scenarios. He tells we should look into data in terms of collections, like standard collections, which helps us writing lambda and functional. We should write more functional. By functional, I mean being more stateless, being more immutable. Then the data actually flows through this set of functions. That's when the data pipeline happens. There are actually three opportunities for doing parallel stuff. And I'm actually thankful to the earlier speaker who talked in favor of concurrency. I should mention that we are using different terms here, but the meaning or what we are talking is the same. So first option is doing parallel processing. When we say parallel, I mean that the data is completely known to us, especially the size aspect. When we do that, we design our algorithms in such a way that things happen in parallel. I have one example that we'll see in the demo later. When we don't know the size of the data, we don't know the actual workload that will happen, then basically we try to be reactive. That's what the earlier speaker was referring to. In that architecture, we put a queue in the front of the application where events get registered. There are workers in the back end who listens to these events and act upon it. I think you remember he mentioned celery and things like that, right? So this is what I call being concurrent and reactive. Then third option is that if we don't want to react to each and every event, then we can choose to react to batch of events. That's what happens when we do stream processing, which is very popular in IoTs, where we do stream processing for batch data from different sensors. Okay, so now Mark does reactive architecture. He's happy. Seems to be the case that he has solved the scalability issues. So he again goes back to the deployment and launches his service. Okay, so wow, the customers seem to be happy. More and more customers are now using the service, and one day, some customer reported a bug. Looking at the symptoms, Mark knows that this seems to be a bug in data access layer. So he goes and fixes that and deploys. Next day, another bug is reported, but this time Mark is confused. He does not have clue what is going wrong. So he has to go and investigate that bug. He goes through the pain that today morning Ludovic mentioned in his keynote, the second keynote I'm referring to. The application is monolithic. So to repro the scenario, he has to configure the whole application, which is a pain. Then after doing the repro, by the way, repro is popular word for reproducing the scenario. Whoever has worked on this will know. So after doing the repro, he will have to attach a debugger. Again, that's a very heavy process. You have to, again, it takes time. Then, okay, so after doing a lot of work, he found the bug, he fixes the bug, but then still story doesn't end. Hard work continues. He has to test the fix. And as Ludovic mentioned in the morning, the testing is also very crucial. For this big application, there could be n number of scenarios, and we cannot segregate the test cases which are just sufficient to fix the given test, to test the given fix. So he has to run a lot of test cases, which takes time. In the meantime, Grace becomes impatient. She asks, how much time do you need more, right? But our friend Mark has a lot of patience. He finishes the test case and then deploys it again. Or he was about to deploy. And then basically he remembers what his professor used to talk about microservices. So Sheer also mentioned about microservices in his talk. And in my opinion, microservices gives you a lot of flexibility in terms of maintainability. Maintaining a big architecture, it's really a pain. If you don't break your application into a set of microservices, which are actually independent chunks, then, as we just mentioned, maintenance, which means reproducing the bug, fixing the bug, testing the fix, and so on and so forth, takes its own toll. So professor told that we should do microservices. And that's what Mark did. He does the microservices and again deploys the service. Okay, awesome. So Grace tells Mark that now we are working fine. How about adding a new feature? So that makes Mark very happy, because as a developer, he was bored fixing the bugs. He wanted to do new feature. So he's very happy. Now he goes and implements this new feature, and he's about to deploy the service again. Now, again, we are coming back to the same point that earlier presenter mentioned. Deployment itself is a task, isn't it? That's what was mentioned in the previous talk. And without container, that becomes really a big task. So that's what Professor also talked about to Mark. He tells that containers are really fast in deployment, and it also gives us opportunity to create a production-like environment in the local setup of the developer, so that there is some confidence that he can work on the actual production environment. Moreover, each service runs in its own environment, so it's isolated and safe. Okay, so Mark does containerization and deploys the service. And then basically, they lived ever after. So basically, that's the story of Grace and Mark. What's the crux of this story? Crux of the story is that current business model demands speed, demands agility. First thing is, there's a need to be experimental. We need to experiment. If it's okay to fail, but we need to fail fast. That's what you would have also heard. Then we also need the ability to react to situation, because not everything can be planned. So the business guys will always talk about these two things, and that actually ends up being, the requirement of speed, agility. But the software has to be good in terms of correctness, performance, maintainability, and operability. So the first 3 points are relevant to developer. But as we all know, we are working in DevOps era. So that's where operability is also a responsibility of a developer. That is where people are trying out cloud native applications, because that all these goals can be achieved in a specific time with a specific budget. So how do we achieve those goals? Correctness. Definitely test cases. There is no other way. But key question is that if I'm running my application in cloud, then how do I test in cloud? Better to test locally, be confident about it, and then deploy. So how do we do it? We'll see that in a demo. Performance. I call this horizontal scalability, which was also mentioned by the previous speaker. And as we just discussed, we have 3 options of parallelization, concurrency, and stream processing. Maintainability. This is where I like microservices. And operability. That is where containers are important. Okay, so this is the example cloud native application that we will go through in the coming demo. I have written a very simple hello world-ish type movie recommendation engine, but that's a cloud native machine learning app. There are actually simple 2 parts. One is offline training job, which basically takes a movie data, trains a machine learning model, and stores it in the cloud storage. The second part is online scoring service, which takes that model from the cloud storage and scores the given user input and generates the recommendations. Okay, so these are the layers that this cloud native applications will have. The core logic will be part of the functionality layer, which is the 3rd layer here. That will have all the functionality or the logic in terms of as much functional code as possible. I'm glad that earlier presenter had also mentioned about it, so I don't have to stress upon it. Then we have data access layer. Again, this is what was talked about in the previous presentation with term called wrapper pattern. This is exactly that. So that we are abstracting the underlying data store. Another layer is basically the output channel. So by output channel, what I mean is that just like input could come from different sources, output can also go to different targets. So why don't we abstract the target also. I mean, we don't need to do abstraction, but we just separate the output channel from the main logic layer. And last but not the least is the deployment layer, which is where either we use vendor-specific APIs or our own container scripts. Let us look at these layers individually. So this is the functionality layer. As I mentioned, we do most of the stuff in functional, and we try to do those parallelization. This layer is responsible for horizontal scalability. As discussed earlier, being stateless is a luxury. So we try to achieve that in this layer. For example, you can imagine there are a set of functions like reading the input data, splitting the input data, transforming into different format, then training the model, and then storing the model. So this is kind of very simple example of a data pipeline, where data goes through a set of functions. Then, as we discussed, there is layer for data access, and we have abstract class, which actually represents a data store, and then we have concrete classes, which are basically the children of this abstract class. And similarly, we have output channel layer. For microservices, this would be REST layer. Last but not the least, deployment layer. Here, we have two options. One is vendor-specific APIs. For example, AWS has an API called run job flow, which basically does everything. For example, it starts the cluster, takes the job, deploys the job, and runs the job. It's all things in one API. So everything is basically abstracted by using one API. Second option is definitely using our own Docker scripts, Docker compose files, YAML files, and so on and so forth. This is useful for container platforms like OpenShift. So this is what I'll be demoing in a bit. Okay, so now let us see a small demo of main points that I discussed in this presentation. One, let us go through the functionality layer, where we are doing a training. Okay, so it might be difficult to do it with one hand. I'll try my best. So as you can see, this is the main functionality. I'm calling it model.py. It has main 4 APIs. One is train, which takes the URL of source data and then trains the model, stores, and returns that model. So as you can see, I decided that this data is known to me. Everything is known, especially the size does not change. So I decided to go for parallel processing. There are many libraries now available. Apache Spark falls in this category very well. So I'm using Apache Spark here. So as you can see, my data comes here as lines. Then I'm transforming it. I'm doing a split on top of it. Then I'm transforming it here. And then in the end, I'm generating a ALS model. Then I'm converting it into, I'm extracting the feature matrices and creating my own model, returning that model here. So this is one example of data pipeline. Then I have another API to save this model to a given data store. As discussed in the earlier presentation, this is a wrapper pattern example. So this data store would be an object of abstract class. So this is the abstract class, and this is the concrete implementation of that class. Okay, then there are APIs to load the model from the data store and keep it in memory. This is going to be useful while scoring the model. And of course, the last API is the score API, which takes the user input and score it on that given model. Okay, So I'll try to do demo using one hand. Let us see. Okay, so as I discussed earlier, it's very important to do local testing before we deploy this piece of code, because once we deploy, only the logging is something. Logging is the information that we will have to know how it is performing, right? So it's very useful and easy in PyCharm. Okay, so we just saw the code. Now, okay. Okay, so this is the test case, right? So I just need to do this. Okay, so now we can go inside the training API and see how it is working. We can do unit testing like this. Okay. So it's important to know and do this kind of unit testing before we deploy the code, because once it is launched, it's kind of literally running in cloud. We don't know how it behaves. We can't check there. So this piece of code I'm running here and testing, right? So this will give me the ALS model. I'm just skipping in the interest of time. Then I just complete my unit testing like this. Okay, so I just tested my code by using local file system data store. But as we have abstracted perfectly, we are confident that it should work on cloud as well, because there we are going to use S3 data store. But it should work fine because we have just isolated the stuff and tested locally. So this wrapper pattern and this kind of unit testing help us do local tests. Okay, so we just did two testing together. One is a training job and the scoring part, right? So now let us see how we can do a deployment. Okay, so basically I'm going to deploy this piece of code in OpenShift cluster. OpenShift is a platform, container platform by Red Hat. So you can deploy your code there and run in the cluster. Okay. Is this readable? Okay, so what I have done is basically I created a new project in my cluster. By the way, like I can show that I'm also logged into my OpenShift. Just a minute. Okay, so this is my OpenShift console, and I just created a demo project which is listed here. Okay, so now basically I need to tell OpenShift to read my code from the GitHub repository. For that, I need to share my SSH secrets. So that's what I did. Okay, so now I have added the secret. In addition to that, I also need to add secrets for AWS credentials. This is what I added just now. Let me just double check whether my console reflects this or not. So if I go inside the demo app, there I can check the resources. So that's what we just did, AWS and Git key. Fine. So now basically we are ready to launch our service here. To do that, we just need a YAML file. I know there is some amount of learning curve, but that pays off, as discussed earlier in the previous presentation. So I have created this YAML file by running OpenShift tools on top of my Docker specifications. Okay, so now we can create. Okay, so now when we say this, then it started building the movie recommended code. And what it builds is basically the Docker images, right? And we can see the log also. Okay, so it might take some time depending upon the network speed, and then it will create the image. Okay, so I'll let it run, and we can discuss one more point that I had planned to discuss. So I'll go back to the presentation. Okay, so in this presentation, we saw many aspects of cloud native application, but we didn't get chance to cover continuous integration, continuous delivery, security, monitoring, etc. Also, I can show the code for using vendor APIs to submit the job on cluster, but we could not demo it in this presentation. The code, the slides, and contact points. The code is in GitHub, and the slides are in speaker deck. Okay, before going into conclusion, let me see what happened here. Okay, so it might take more time depending upon the network speed. I'm downloading quite a bit of things here from this network. Anyways, if you allow me, I can use another service that I had already deployed in a different project. Okay. So this is the beauty of Kubernetes. You can deploy it once, and then you can scale it by just using a single click. This is what OpenShift gives you the power. You can run the show using a console. So I would suggest or recommend you check it out if you are looking for, Docker, Kubernetes kind of environments. Okay, so this is the API. If you remember, there is a health check endpoint in this piece of code. Okay, let me show that. So this scoring API has heartbeat or health check API, which just says status okay, which helps us check if everything is running fine or not. And it actually, before running any API, it will load the module from S3 data store. Again, here you can see that our wrapper pattern helps us in this way. This is the data store class or object that I'm passing, right? And then of course there is a API for doing recommendation. So let me show you that once. Okay, so that was a get call. Let me do this. /API/v1. Recommend movies. Okay. V1 recommend movies. Okay, so there seems to be some problem, or there seems to be some bug that I have to react to. But anyways, the purpose of the demo is deployment, and that's how we can deploy, right? So let me go back to the slides. Yes, I'm almost done. Okay, so conclusion. So as we just discussed, business demand is speed and agility. We have to work with a given budget, and we need to have the ability to experiment new ideas. We also need the ability to react to different situations, because not everything can be planned. And this is where cloud native applications could be a good solution. We saw different layers involved in cloud native applications, and also techniques to achieve the required agility and speed. And most importantly, everything was written in Python. And it has been discussed in many presentations here, but Python suits very well in this area also. Yeah. So yeah, so that's it from my side. I'll be happy to answer any questions if you have. Thank you.